Applications of double integrals. Density and mass. Suppose we have a region in the xy plane, and suppose that at a given point xy, we can define the density at that point as some function rho of xy. This is particularly useful if you imagine a flat object that has a particular shape that is irregular in terms of its density as you move around in that shape. If that is the case, then at a particular point, it could be heavier than at another point. The way we find the mass at a particular point is we take the density at that point and we multiply it by the area right around that point. So we have the function rho of xy multiplied by delta A, which is the area. Now, if we add up all such delta xy's multiplied by their respective areas, so consider lots of little squares. If we add all those up, we end up getting the total mass of the object. The function rho does not have to represent density. It could measure anything that changes from one point to another. So we could have the charge on this surface, and that charge could vary depending upon where you are on that surface. That's just another example of how we can use this concept. Suppose charge is distributed over the triangular region D here, so that the charge density at xy is some function sigma of xy equals x times y. And this is measured in coulombs per square meter. Find the total charge. So in essence here, we just need to integrate the function sigma of xy with respect to the area over the region D. So of course, we could integrate with respect to x or with respect to y first. It doesn't really make much of a difference. In cases where it doesn't make a difference, I prefer to integrate with respect to y first. So here we can see that y varies from 1 minus x up to 1. And then x varies from 0 to 1. So we're going to have the integral from 0 to 1 of the integral from 1 minus x to 1 of our function sigma, which is x times y, dy dx. So let's go ahead and perform the integration on the inside there. So this right here, when you integrate, is going to be x y squared over 2. This is going to go from y equals 1 minus x to y equals 1. And then we'll do this with respect to x. So this is going to be the integral of, now when I plug in y equals 1, we get x over 2. Minus, when we plug in 1 minus x, we get x times 1 minus x squared over 2 dx. So now we need to multiply this out. Notice that I could pull out the 1/2 here. So this is going to be 1/2 integral 0 to 1. Then we have x minus, and then when we multiply this out, we should get x minus 2x squared plus x to the third. And all of this is with respect to x. Simplifying, we have the integral from 0 to 1. X minus x cancels. Negative negative here makes a positive 2x squared. And then we have negative x cubed dx, and then a 1/2 on the outside. So let's go ahead and integrate. We have 2x to the third divided by 3 minus x to the fourth divided by 4 from 0 to 1. And this is going to be 1/2 times 2/3 minus 1/4. And this is equal to 5 over 24. And this is measured in coulombs. So put a big C here. Here we go. We can also talk about the center of mass of an object. So imagine we have a two-dimensional object. So we'll consider it to be flat. And suppose that the density of the object changes depending on where you're located. What we'd like to do is find the center of mass, which means that if we were to place a fulcrum underneath this object, the object would balance when you put it on that point. Now we'll skip some of the details here. So if the coordinates of the center of mass is x bar, y bar, we can find this center by taking the moments around the y-axis divided by m. That turns out to be this formula here. And then for the y-coordinate, we can take the moments around the x-axis divided by m, and that is this here. And then m, of course, is the total mass of the object, which we already saw we get by taking the double integral of the density function. So let's go ahead and take a look at an example. So here we'd like to find the mass and the center of mass of the triangular lamina with vertices at points 0, 0, 1, 0, and 0, 2. If the density function is given by rho equals 1 plus 3x plus y. Okay, so first let's go ahead and find the mass, m. We're going to get this by taking the integral over our region of the function rho of xy with respect to area. Now let's go ahead and determine which variable we want to integrate with respect to first. I'm going to do the y variable. So the y variable clearly varies from y equals 0 up to y equals 2 minus 2x. Now this is given to you here, but you could find this by simply finding the equation of the line that goes through these 2 points. So we're going to have the double integral. Again, y varies from 0 to 2 minus 2x. On the x-axis, we can see that it varies from 0 to 1. Put in our function 1 plus 3x plus y with respect to y and then with respect to x. Go ahead and integrate now. So the integral of 1 with respect to y is y, and then plus the integral of 3x with respect to y is 3x times y. And then the integral of y with respect to y is y squared over 2. And this is going from 0 to 2 minus 2x. And then with respect to x. Now keep in mind, these are y values, of course, so we're going to plug this in for y. Also, notice when you plug in 0, you get nothing. So we only have to plug 2 minus 2x in. So this becomes the integral from 0 to 1 of 2 minus 2x plus 3x times 2 minus 2x plus 2 minus 2x quantity squared divided by 2. Oops, I guess I have an extra parentheses in there. I'll go like that. There we go, dx. All right, now let's go ahead and simplify here. So we have the integral from 0 to 1. We've got 2 minus 2x plus 6x minus 6x squared plus, and then when you multiply out this part here, you should get 4 minus 8x plus 4x squared. And when we divide all those by 2, we get plus 2 minus 4x plus 2x squared dx. So now we'll go ahead and finish this up, combine some more terms here. So we have 2 plus 2, which is 4. And then we'll combine all of our x terms. We have negative 2x plus 6x minus 4x. And that's all going to cancel out pretty nicely. And then finally, negative 6x squared and positive 2x squared is negative 4x squared. Integrating, we have 4x minus 4x to the third divided by 3 from 0 to 1. And this is going to be 4 minus 4 thirds, which is 8 thirds. And remember, this is the total mass m. So now we just need to apply these formulas to get the center of mass. So let's go ahead and do the first integration. Now the good news is we're integrating over the same domain, so our limits of integration will be the same. The other thing is 1 divided by m is going to be 3/8. So x bar is going to be 3/8 integral 0 to 1 integral 0 to 2 minus 2x. And then we have x times rho of xy, and rho was 1 plus 3x plus y, and then this is dy dx. So we have 3/8 integral 0 to 1. If we multiply this out, we're going to have x plus 3x squared plus xy. And now when I integrate that with respect to y, we're going to get xy plus 3x squared times y plus xy squared divided by 2. Now again, remember this gets evaluated from 0 to 2 minus 2x. And then when we're all done with that, we'll integrate with respect to x. So let's go ahead and perform the integration. We have 3/8 integral 0 to 1. Or actually, we already did the integration. Sorry. We're going to substitute now. So we have x times 2 minus 2x plus 3x squared times 2 minus 2x plus x times 2 minus 2x quantity squared divided by 2. Okay, I'm going to multiply this out and combine like terms, but I'm going to do that off camera because that's a bit of tedious work, and then you can check it. All right, so here we are, simplified quite nicely. Now this is 3/8, and we'll perform the integration here. Integral of 4x is 4x squared divided by 2, which is 2x squared. And then minus 4x to the 4th divided by 4, which is x to the 4th. And this goes from 0 to 1. And this is 3/8 times 2 minus 1, which is 3/8. So the x coordinate of our center of mass is 3/8. Then we do the same thing to find our y coordinate. Just a slight change in the formula here. Instead of an x here, we're going to have a y there. So let's go ahead and go through and do that calculation. So again, the only change is the x became a y here. So now we're just going to multiply this out, and then we're going to integrate, and we should be able to come up with the answer by going through the same work. And here is all that work, and when you simplify your answer in the end, you do get 11 over 16. And so now we know that y bar is 11 over 16. And so our center of mass is the point 3/8 and 11 over 16. And here's all the work for that if you want to pause the video and double check everything. And then you can see there is the center of mass, which was already in the diagram, just for completeness here. And that means that if you were to take this as a two-dimensional sheet and put your fulcrum right on this point, this would balance on that point. In this problem, we're told the density at any point on a semicircular lamina is proportional to the distance from the center of the circle. So this means that if we have some point, let's say x, y, and we know the distance from the center of the circle is the square root of x squared plus y squared, right? Because that's just the distance between the point xy and the point 0, 0. We know that the density at that point is equal to some constant multiple of this distance. So I'm going to say k times the square root of x squared plus y squared. That's what it means to be proportional. So now the mass is going to be the double integral of this density function, which is k times the square root of x squared plus y squared. And then we're going to have dy dx. Now, y is changing from here up to here. So I'd have to solve this for y, and then x would be changing from negative a to a. So if I do that, I'm going to get the square root of a squared minus x squared up here. But notice that this integral is kind of challenging to do, right? This is not a simple integral. This would require trig substitution. So instead, what I'm going to do is integrate this in polar coordinates. So in polar coordinates, theta is changing from 0 to pi. So we can go ahead and plug that in. R goes from 0 to a. Then we have k times, now let's remember that r is equal to the square root of x squared plus y squared. So this in polar coordinates is just r. And then don't forget, you have to multiply by r dr d theta when you change to polar coordinates. But this just becomes the integral from 0 to pi, integral 0 to a, k r squared dr d theta. Integrating, I can pull out the k. I have integral from 0 to pi, and the integral of r squared dr is r cubed over 3, and this goes from 0 to a, and then d theta. And so we have k times the integral from 0 to pi. Here I just need to plug a in, so we get a cubed over 3 d theta. And that's just a constant. So I have k a cubed over 3, and then the integral of d theta is theta, and this goes from 0 to pi, and plugging in pi, we get k pi a cubed over 3. And this is the mass. Now we can use this to find the center of mass. All right, so now let's go ahead and find the center of mass. So we'll find x bar and y bar by applying these formulas. Now, once again, we're going to integrate in polar coordinates. So 1 over m is going to be the reciprocal of this fraction here. X, remember in polar coordinates, x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And rho of xy is k times the square root of x squared plus y squared. In polar coordinates, this is going to be k times r. So, integrating for x bar, we're going to get the following. And we just need to do a little simplifying here. Notice that one thing we can do right away is the k here can cancel the k on the outside, since those are constants. And then we have r to the third times cosine of theta, dr d theta. Both of our variables are being integrated over a constant interval, so we can just separate these into two separate integrals. And here is what that looks like. And then we just need to perform the integration here. So 3 divided by pi a cubed multiplied by, we're going to have sine of theta from 0 to pi multiplied by r to the fourth over 4 from 0 to a. Evaluating these integrals, we're going to get 0 right here because sine of pi is 0 and sine of 0 is 0, right? So just fundamental theorem of calculus. And then applying it right here, we're going to get a to the fourth over 4. Doesn't really matter, though, because this whole thing is going to be 0. Now when we find y bar, everything is going to be the same except we're plugging in y, and y is r times the sine of theta. So the only thing that's going to change here is this cosine is going to become a sine, and then everything else is identical. So let's go ahead and try to squeeze in that change. So when getting y bar, the k's are still going to cancel. The cosine became a sine. We can still separate the integrals. The integral of sine is negative cosine. And right there, we're going to have negative cosine of pi minus negative cosine of 0. This is negative, negative 1 minus negative 1, which is 2. So I bring that value in here. And now if I simplify, 2 goes into 4 2 times. a cubed goes into a to the fourth a times, and we end up getting 3a divided by 2 pi. And this is the y-coordinate of the center of mass. So remember, the x-coordinate, x bar, was equal to 0, and the y-coordinate is 3a over 2 pi. And you can see that point right here. We can also use double integrals to find the moment of inertia about the x-axis, the moment of inertia about the y-axis, and the moment of inertia about the origin. One thing to point out, if you look at these formulas, is the moment of inertia about the origin right here is basically equal to the moment of inertia about the x-axis plus the moment of inertia about the y-axis. So here we want to find the moments of inertia Ix, Iy, and I0 of a homogeneous disk D with density rho of xy equals to rho. All right, so we have a constant density function, and we have a disk, which is basically a circle. The center is at the origin, and the radius is a. So let's go ahead and take a look at the region. We have an x and y axis, disk of radius a, center at the origin. Ix is going to be the double integral over this region, y squared times rho times dA. Iy is the double integral over the region, x squared times rho times dA. And then we'll just add these together, and that will give us the moment of inertia about the origin. So we're just going to do Ix plus Iy. All right, let's go ahead and set these up. So Ix is equal to the double integral. And once again, we're going to use polar coordinates. It's much easier to use polar coordinates. Theta goes between 0 and 2 pi. R goes between 0 and a. We have y squared, which is r sine of theta, quantity squared, times rho, but then times r dr d theta. And so this becomes the integral from 0 to 2 pi, integral from 0 to 2a, 0 to a. There we go. And then we have r to the third power, sine squared of theta, dr d theta, and the rho is a constant, so I can actually bring the rho all the way out to the front. And we can separate this into two distinct integrals. So the integral of sine squared of theta d theta multiplied by the integral of r cubed dr. Okay, now the integration, this requires a half angle identity, 1 minus the cosine of 2 theta divided by 2. Then we have to integrate that, and then this one here is pretty straightforward integration. So let's go ahead and do that work off camera. Okay, and so there it is in all its glory. And then if you think about it, for Iy, we're just going to have an x squared. X is our cosine of theta, so this sine here will become a cosine. That means we'll have a cosine squared, which means this will be a plus right here. And that is literally the only difference. Okay, so when we go to compute Iy, we are literally only going to have a plus there. So it's going to be 1/2 rho. That value is still going to be 2 pi, regardless of whether the minus changes to a plus or not. And then a to the fourth over 4. And so what you see here is that you get the same value. So what we have is rho pi a to the fourth over 4 is the moment of inertia about the x-axis and about the y-axis, and the moment of inertia about the origin is just rho pi a to the fourth over 4 plus rho pi a to the fourth over 4, which is just rho pi a to the fourth over 2. And that concludes this video lesson.